interior decorations, clothing, and in personal arts and crafts. However, while designing these patterns is difficult, even choosing colors for these patterns can be challenging. One reason for this is that it can be hard to visualize what a coloring will look like beforehand. For example, let's say I want to color in this pattern. I like nice cool colored patterns, so I might start out with an initial coloring that looks like this. Well, this coloring is definitely cool colored, but it definitely looked better in my head than on the screen. So to fix this, I might make a series of tweaks, like darkening the blue to make the foreground stand out, or weakening the pink to make it less bold. So this looks better, but now I'm stuck. The coloring looks okay, but it's not quite what I want, and I'm not sure what to do next. There is actually a nice mellower coloring a few tweaks away, but I'm not really sure how to get there. By making local tweaks, it can also be difficult to explore other farther away, but also interesting options. For example, these warmer colored patterns. The gold one is actually pretty nice, and it's not something that I might have thought of beforehand. So, how can we better explore the coloring space? Can we have a computational tool help us out? In this project, we focus on suggesting pattern colorizations to facilitate the coloring process. We want a system that takes as input a pattern template, where in this example, each different gray level indicates a unique color that can appear in the pattern. The system should also take into account any user preferences on types of colorings, and output a set of appealing colorings of the input. In particular, the system should be able to suggest diverse colorings for users who are uncertain about their preferences. It should also allow users to refine their suggestions as they gain a better idea of what they want, as well as accommodate different stylistic preferences. So while I may like cool colored patterns, my friend may like warmer colored patterns. So first of all, what do we mean by pattern template? In this project, we focus on patterns such as the one on the left. A pattern template specifies a number of color groups, which are spatial regions that must map to the same color. For example, one color group in this pattern is the white background. Another group corresponds to the red regions in the pattern, and so forth for the other three colors. Changing the colors of these groups will then recolor the template. We can author templates like these from existing colored patterns, vector art, or other types of segmented images. Related work has focused on color compatibility. Color compatibility is a classic problem where people have developed systems and theories to predict what combinations of colors work good together. More recently, O'Donovan and colleagues analyzed online data sets of themes and their user ratings. They introduced a regression model to quantify the compatibility of 1D color themes. This model can be used to detect and generate appealing color themes, such as the one on the lower right. However, when it comes to coloring in patterns, color compatibility should also take into account 2D spatial arrangement. For example, these are some highly rated color themes, which look good as 1D themes. However, when applied to 2D patterns, they can create some controversial colorings, where the foreground might blend into the background, or the background might be considered too loud or overly saturated. Finally, some people may have different preferences for coloring style. Some may actually like this bolder style coloring, or ones with more delicate contrast. So how can we learn to make good pattern colorings while also taking into account personal preferences? One option, and the approach we take, is to look at examples of desired colorings for guidance. There are many nice patterns available on the web which show what colors artists put together, which are used as backgrounds, which are used next to each other, and so on. By simulating similar properties in our suggestions, we may be able to generate appealing colorings. So here's what our pipeline looks like. Given an input pattern template, a set of colored pattern examples, and optional user constraints, the system learns a model to predict which colorings of the template are more desired. Using this model, the system suggests a set of diverse colorings. And since the system learns properties of desired colorings from examples, we can change the style of the suggested colorings by just changing the set of examples. So if I like dark and glowing colorings, I can provide a set of such examples to get similar styles in suggestions. So in this project, we draw our examples from an online pattern sharing site called Color Lovers. There are many color patterns available on the site from different artists. We were able to collect 8,200 patterns from the top 82 artists, though many more exist. For our experiments, we trained models on up to 913 of these patterns. So using these examples, we can now learn how to suggest good colorings. But first, we must have a way to quantify the goodness of coloring. Here we'll give a high-level overview of our model. So to illustrate how this model works, let's take this pattern template as an example. We want a good coloring of this template, and there are many different factors that might constitute a good coloring. The simplest is just to consider each color group in the pattern by itself and its assigned color individually. For this, we insert scoring functions over each group, or Unary factors, that score how well individual colors fit each region. So if we assign this flower group, for example, this mellow red color, the Unary factor on this group might consider it a good color for this region. So how do we determine if this color is good? Well, if we look at our pattern examples, we might find that similarly shaped regions are colored in a similar red. So it's likely that this color is appropriate. On the other hand, bright neon green might be considered a poor choice for this region, since few examples in our data set use this type of neon color in the foreground. So far our model has Unary factors that consider the goodness of individual colors. However, this is not enough. We could hypothetically color both the foreground and background in a similar mellow red. So while the Unary factors think the colors look good individually, we can barely separate the pattern regions. Thus, our model needs more sophistication. To handle this, we add additional scoring functions, or pairwise factors over adjacent color groups. These score how well two combined colors fit each set of adjacent regions. Using these pairwise factors, we can detect that this combination of similar adjacent colors is a poor choice. Finally, we may want to consider colors more globally as well. Here, both individual colors and pairwise adjacent colors look reasonable. But as a whole, the color theme of this pattern may look a bit off. We include a global color compatibility term to score the color theme of the pattern. Here we use the color compatibility model introduced by O'Donovan and colleagues. We can now improve the color theme of this coloring, like so, to find a coloring that is scored highly by the factors overall. So our final model includes factors that consider individual colors, adjacent colors, and the global color theme of the pattern.
Diving into how we implement the sort of the simplest factors, the Unary color factors here. These are supposed to score the goodness of a single color in the pattern, and the way we're going to approach this problem is to look at it from a probabilistic standpoint. So given the training examples that we have, we want to be able to answer the question, how likely is this color, given features of the shape of the region the color is assigned to. So to make this model a bit more generalizable, rather than modeling this probability distribution for the color directly, we're going to model it for several key properties of the color, such as its lightness, its saturation. There's an interesting property we use called name saliency, which was developed by some of our colleagues at Stanford, which is a measure of how reliably a color is named. And it's designed to kind of reflect how instantly recognizable a color is. So if there's one color that, say, everyone in the world calls red, that will have a very high name saliency. But if there's another color that some people call red and some people call maroon and some people call burgundy, then that will have sort of a lower score. All right, and the shape features that we consider are things like how big is the region, Is it relatively compact or elongated? Is it located centrally in the middle of the pattern, or is it somewhere off on the fringes? There's another list of features that we use as well. There's a more complete list described in the paper if you're interested in the set that we use. But it's things of this nature. Okay, so how can we learn this kind of probability distribution from our examples and then use it to score color assignments? So by way of example, suppose we're trying to learn the distributions over saturation. So what we'd like to be able to do is feed in our example patterns and obtain a predictor which, if we give it a particular shape feature vector, say for a region that's not very big and fairly skinny, located kind of in the middle of the image but not too close, et cetera, et cetera, this should be able to output a predicted distribution over the saturation values we would expect to see of a color in that region. And then when it comes time to actually score a color assignment, we can query this distribution with a particular value and then get back a probability, which we can use as a score. So this is kind of the high-level plan of how we'd like this to work. But now we have to answer the question of how are we actually going to implement this process? So again, by way of example, suppose I'm trying to learn a probability distribution over lightness. The first thing I'm going to do is actually discretize the range of possible lightness values into a set of bins, which is going to make our problem a bit easier. Now, if I go and I look at all of my example patterns, and I look at each region in the pattern, I can extract the shape feature vector for that region, as well as the lightness value of the color that happened to be assigned to that region in the example. Question?
With all these probabilities, what is the universe you're drawing from? How do you know when one is more likely than is there a world of colors, or how do you describe that?
Right, so the color space we operate in is the LAB color space. So it can be any color that's representable within that basis. And the likelihoods, as I'm going to show, are going to be modeled based on which colors occurred more frequently in the examples.
In the examples?
Yes, exactly. Okay. Okay, so if we take a look at this particular pattern, the lightness value for this region would fall into this bin. So we will say that this region has discrete lightness value 1. And then similarly, this region had value 2, and this one has value 7. So what I've done basically is I've gone through and I've taken each of these continuous values and turned them into labels. So essentially I've turned my training data into pairs of labels and feature vectors, which is exactly the kind of data that you can use to train a simple classifier, to predict, given a feature vector, what bin its lightness value should fall into. And in our particular model, we used a multinomial logistic regression classifier. And the point of having this is that if we're given an uncolored pattern template where we know what shapes are in this pattern, so we can compute all their shape features, but we don't know what their lightnesses should be, we can ask our classifier to predict, for any given region, the probability that its lightness value should fall into each one of these bins. So this gives us a histogram that might look something like this. And then what we can do is we can smooth this histogram by convolving it with the Gaussian kernel, and this recovers sort of an approximate continuous probability distribution. And this is finally the actual distribution that we're going to use to score colors. So just to give credit where credit is due, we didn't completely come up with this idea of histogram estimation and smoothing. This was inspired by some recent work in automatically colorizing grayscale images, where the authors of that work tried to predict the color of a pixel given the texture of a patch of pixels around it. And it tended to work pretty well for them, so we thought we might as well apply it here as well. Okay, so here are a couple examples of some distributions over lightness that we actually learned from some of the patterns in our training data set. And in these two plots, the pattern region whose probability is being visualized is colored in an orange. So the interesting thing to note here is that for the large sort of background region in the top example, the distribution that we predict is kind of bimodal. This is sort of mirroring our intuition, I think, that the background of an image like this is either usually going to be light or it's going to be dark. But it's not typically of middling intensities, because that would tend to sort of conflict with the foreground. And the ability to capture this kind of bimodality, we think, is one of the major advantages of this histogram-based representation that we used. over simpler models we could have used, such as a linear Gaussian. Okay, so jumping back up to our model overview, I just talked about how the unary factors are implemented. These pairwise factors are actually implemented using the exact same learning framework. There's some mechanical details that are different. The shape features that we learn based on are actually concatenations of features of two adjacent regions, and the color properties that we try to predict are not properties of a single color, but properties of two colors, things like relative lightness or relative saturation. Other than that, all the machinery is the same. And of course, as Sharon already mentioned, this global color compatibility factor uses the model that was developed by O'Donovan. Okay, so then the overall score of a pattern is really just the product of all of these factors. It's pretty simple. And this forms a type of probabilistic model known as a factor graph, which some of you might be familiar with. But the precise math behind this formalization, and as well as the algorithm that we use to tune the relative weights of each of these factors, I'm not going to describe it in detail here, but it's in the SIGGRAPH paper that we published on this work. So if you're interested, definitely go check that out. And speaking of tuning the relative weights of each factor, Sharon's going to talk a little bit about some of the factors that we found to be significant in the experiments that we did.
So on our training data, we found a few factors that stood out in our model and carried a lot of weight. So these are a few of them: color compatibility, perceptual distance between adjacent regions, color name counts, and the saturation. And to give an idea of how our model tends to score things, I'll just give a few examples of each. So the global color compatibility of the pattern's color theme was just developed by O'Donovan and colleagues' work. And they looked at user ratings of color themes, and so they share a few of the similar features as we use, such as what is the lightness of each color, but they also consider, collectively, what is the diversity of colors in this color theme. And since this term carried a lot of weight, what we can learn from this is that, well, if the coloring has a good color theme, it's most likely to be pretty good initially. So in addition, we found that our model prefers a certain amount of perceptual distance between adjacent regions, but not too much. So as an example, let's take this flower pattern again. We have two regions highlighted in orange and green, which we're looking at. And we see that between these two regions, there is a certain amount of distance that tends to be ideal. So the bottom two color bars show an increasing amount of perceptual distance between the bottom blue color bar and the top bar. And the highlighted difference here is just around the predicted ideal between these two adjacent regions. We don't see very many, as much mass where there is a greater contrast, because it could be considered too jarring.
Question?
Yes.
Is that like the minimum distance or some kind of average distance along some? How do you measure distance for regions?
Right. So the question is, how do we measure distance between regions? So here we're just looking at the color assigned to each region. So the background has one color, we say, and this green region also has one color. And we just look at the Euclidean distance in LAB space between the two colors. And we say that's the perceptual distance. Oh, yes?
Does that mean basically the minimum acceptable contrast between those two colors?
So it's not really, it's not a hard constraint. This is just if the difference is, say, around 0.2, then it'll receive a higher score from that factor. If it's larger, it'll just receive a falling score. So it doesn't explicitly enforce that it should be that distance, but it tries to bias the colorings towards that distance.
And as far as the issue of contrast, there's a lot of different ways that people have tried to quantitatively evaluate contrast, and this is not exactly getting at that notion, but it's similar. So, yeah.
Thanks for the questions. So in addition, we found that color name counts. This predicts the color category of a region. Was also important. So for the previous factor, we didn't actually see much difference between in the factor between different adjacent regions. But for this factor and others, we see there's a difference depending on what region we're looking at. So for this orange background region, for example, we see that color categories like red and pink and orange tend to be less preferred, while color categories like black, yellow, and grayish-green are more preferred. On the other hand, for the foreground, there's a much more uniform distribution among the color categories. It doesn't really matter so much if the foreground flowers are red rather than, say, black. Finally, we have the saturation of a region. In this example, the orange background is preferred to be less saturated, while the foreground flower tends to be more saturated so that it can stand out from the background. So these were just some examples to give an idea of what sorts of colorings our model tended to prefer.
So up to this point, we've described how we can compute the score of a given pattern coloring under the model that we proposed. So now we have to talk about how we can use this model to actually generate colorings, hopefully high-scoring ones, to suggest to our user. So to do this, we turn to the Metropolis-Hastings algorithm. And this is something that can approximately sample from this probability distribution that our model is encoding. So Metropolis-Hastings is a Markov Chain Monte Carlo sampling technique. The way that it works is it kind of moves through the coloring space via a random walk. So in our implementation, we let it randomly perturb colors or randomly swap colors of two different regions. And the idea is that this starts with some initial coloring and makes these randomized perturbations until it gradually arrives at better and better colorings. Now the problem with methods like this is they can really easily get stuck in local optima. So to combat this, we use another technique called parallel tempering. What this technique does is it runs multiple instances of this Metropolis-Hastings algorithm in parallel with different global weights on all of the factors. So the way you can interpret this is that the weights, the chains that have really, really low weight are less constrained. So they can sort of freely move around the space of possible colorings. But the chains that have high weight, they're very tightly constrained. So all they can do is kind of locally optimize around a very small part of the coloring space. And it turns out that alternating between these two behaviors of sort of free exploration versus local refinement tends to produce better colorings overall.
Did you consider simulated red, which would seem to have similar properties?
Yeah, it does have similar properties. I think parallel tempering is particularly nice in this case because simulated annealing, as you run it, tends to converge on a single optimum, and so the way to generate, we want our system to be able to generate and suggest multiple different possibilities to the user. To do that with simulated annealing, you'd sort of start multiple different runs of simulated annealing from scratch. Whereas with parallel tempering, you can run a bunch of them actually in parallel on the machine, and then in the end, every single one of those chains will have an interesting different possibility. So it's just one way of parallelizing. They also, the different chains get to communicate with each other, which shares a little bit more statistical information. But they tend to, you could also use simulated annealing as well. I think it's also a valid alternative. Okay, where was I? Oh, right. So finally, we want, like I just mentioned, we want to be able to suggest a diverse set of colorings to the end user. So the way we do this is we take all the samples generated by our sampler and we return, say, the top n of them, where n is some number that's chosen by the user. And what we use here is this maximum marginal relevance criterion. This is sort of a technique from information retrieval, which balances, you want to have all of the things you return have high score, but you also want them to have some variety as well. And we approximate variety by looking at color space similarity between the different colorings. Okay, so that's basically a fairly high level but complete summary of how the system works. So I'm going to go ahead and take a look at some results that we generated. So we mentioned that sort of for early in the creative process, we'd like our system to be able to suggest a variety of possible colorings to help people sort of explore the space of possibilities. So, for example, if we're given these two initial uncolored pattern templates, here are 10 different suggested colorings that our system created. And the important thing to note here is that these suggestions have a pretty wide variety of styles, ranging from more light colors to dark colors, or more bold to muted. And the reason they are such a wide variety is because we trained this model on many different artists from the Color Lovers dataset. So in some sense, it's capturing sort of a broader set of artistic preferences rather than a more focused one. Now, if someone has a better idea as to the kind of coloring they're looking for, then our system can help them refine it. So again, if we're given these two initial colorings of a pattern template, then we can use our system to generate recolorings by adding in just one additional term that encourages each region to take a color similar to its initial color. And you can think about this as sort of a soft constraint that allows all the colors in the pattern to vary, but it sort of prevents them from wandering too far from their initial position. Now, another way that you can do refinement is if you sort of know exactly what color a particular pattern region should be, but not so much what the rest of the image should look like. So what I mean by this is, so for this bird and flowers template, here are 8 colorings that were generated freely with no additional constraints on our model. But if I'm totally sure that I want the flower stem to be a particular shade of green, then I can fix those regions to be that color, and I allow the rest of the colors to vary freely throughout the suggestion process. And so even with the stem color fixed, there's still a lot of interesting variety that the system is able to exploit and to show me. So given these sort of initial suggestion, refinement through soft and hard constraints, what we're going to do now is Sharon's going to come and show a little demo of an application that we wrote that shows some of these technologies working in an interactive setting.
I've seen some nice static image results. So now let's take a look at the suggester in action. Alright, so I'm going to open up a vector image. So far we've seen patterns that are pretty abstract and more stylized. So this is an example of an image that's a little bit different, and it's more like character art. For starters, let's see, well, what does our system do with this image? Sorry, I'm trying to All right. So we're now generating suggestions, and we get, well, a lot of zombie-like colorings of this character. Well, one reason for this is that, well, it's really hard for the computer to know that this is a person and that skin color should really be skin color and not some arbitrary other color. Even if the colors do look good on an abstract pattern, if you change the skin color, then you'll get aliens and zombies. So as a user, I kind of know that this part of the image is important, so let's just fix this region to be its original color. Similarly, if eye whites are not white, then it also looks a bit weird, so let's fix the eyes to be white and the pupil to be this dark blue. And paper to be white. And let's try this again. Alright, so I fixed the skin color and the eye color and the eye whites. Okay, this looks less alien-like. We have some interesting hair dyes. And this does look a lot more reasonable. Actually, this red hair looks pretty good. I didn't think of using red hair. It's still kind of weird. Like, you could have multicolored lipstick, but that still looks a bit odd. So I'm going to change the lips to be red again. I might not care what shade of pink this is. So let's say it should be pink, but maybe not really this shade. You might notice that in this coloring suggestions, both the hair and the shirt were colored in the same color. And that's because in the original image, they were colored both in black. But practically, they don't really need to be the same color. So I'm going to put the shirt in a different color group. And I don't know, I like orange hair, so let's look at other colorings with orange hair and generate more suggestions. Alright, so you get suggestions that fit orange hair. And actually, I think this one looks pretty nice, so let's stick with this one. And now to get back to PowerPoint. Did that work? Okay, great. So now we've looked at how our color suggester can suggest a variety of different coloring styles. So now Daniel will show some more results on how to suggest, on how the color suggester works on more focused styles as well as other applications.
So one interesting property that I think I alluded to earlier is that the system can capture a particular desired style by just manipulating which examples we use to train it. So here we show one example pattern for each of 4 different styles. We have, we're going to call these styles light, dark, bold, and mellow. So by training on a small set of similar patterns for each of these styles, we can generate suggestions such as these, which reflect sort of the most important stylistic properties of their respective examples. And the cool thing about this is that there really were no other tweaks to the model we had to make to capture this sort of behavior, other than just changing the set of input examples that we fed into the system. Okay, we also applied this recoloring idea to a web design problem, where we tried to color the background pattern of a web page to match the body of the page, which had already been colored. And to do this, we just added another term that encouraged each color to be similar to one of the body colors. And so you can imagine that this kind of application could be useful for, automatically retheming a website according to the season or time of day or just any kind of user preferences that someone might have. We also tried a simple fashion design task. We were kind of getting a little bit out there with this one, but so here what we did is we had this 3D model, and we performed recoloring on the 3D model's texture atlas, where we treated the regions for the hair, the skin, and the eyes as fixed color constraints, and then we allowed the color of the pattern on the shirt to vary freely to try to produce a coloring that would match. And we got some decent-looking results, we thought. Okay, so we've shown some interesting results, but we wanted to also verify that our system can consistently produce useful colorings. And to do this, we wanted to evaluate it using sort of a formal judgment study with human participants. And the way we did this is we had participants look at an interface containing 16 recolorings of the same pattern. Now this was condition blind, but unbeknownst to them, 4 of these patterns were just generated by randomly sampling at uniform colors from the RGB color cube, so just purely uniform random colorings. 4 of them were created by sampling from a simplified model that only used the global color compatibility term, so basically treating the pattern as if it was just a one-dimensional color theme. 4 of them were sampled from our full model with all of the factors that we described earlier, and 4 of them were actually hand-colored by artists from the color lovers community. What we asked our participants to do was to choose their 4 favorite colorings out of the set, as well as their 4 least favorite colorings. Just trying to get a feel for, in general, which types of patterns they preferred and really disliked. And when we looked at the results of the study, there's a few things that stood out to us. The first thing we noticed is that people did significantly prefer the colorings generated by our model to those generated by the other automatic methods. So much better than purely random colorings, and also significantly better than colorings that were generated by treating the pattern as a 1D color theme. And this is not surprising. This is sort of what our model is designed to do. Now, also not surprising, patterns that were colored by human artists were preferred to our automatically generated ones. This is, again, totally expected, and we think it's pretty acceptable, because as we've just shown in the demo that Sharon showed you, we kind of envision our technology not being standalone, but being part of an interactive workflow that tries to augment human creativity rather than trying to entirely replace it. Now, another thing we noticed is that if we take a look at the colorings that people marked as least favorite, the ones they really didn't like, our method generated as few of these as artists, sort of human artists, did. And so, you know, our model is not quite generating automatically results that look as good as human artists, but it's not generating results that look any worse than ones that people can make as well. And so we think this supports the notion that our system can consistently generate colorings that are good enough for a person to take and use as inspiration for future creative work. Okay. Well, that being said, there's still a lot of work to be done in this space. We're nowhere near sort of answering all the interesting questions. As became abundantly clear in Sharon's demo with recoloring the image of the student, our system has the limitation that it does not know anything about the semantics of the pattern regions. So for this pattern template, it might suggest this coloring with this pale blue sky, but it could also equally well suggest this one with this non-physically red sky. And this kind of deviation from reality can be artistically desirable, but not in all cases. So we've seen one solution to this of simply, you know, constraining what a color should be. But another interesting possibility we'd like to explore is providing these semantic label constraints where a user can say, this region is sky, and then have that label implicitly constrain the colors that actually get suggested. So one way you might imagine implementing this is by firing off, say, an image search using the keyword sky, and then trying to make that pattern region take colors that occur frequently in the resulting images. Now, additionally, our system is restricted to operating on patterns whose color groups are known in advance. And so what I mean by that is, you know, in this pattern template, the system has to be told that all of the black regions take the same color, all of the lightest gray regions take the same color, etc. And these kinds of representations can be authored from sort of arbitrary vector art, but it can get tedious to do it for images as complex as these, for example. And there's a huge variety of interesting unstructured line art like this that's available out on the web and in the wild. And it would be really cool if we could enable sort of automatic coloring suggestion for these kinds of images as well. But doing this is going to require development of a lot more sophisticated sampling algorithms than the one that we presented in this project. So now, along these lines of some interesting future work that our group is currently exploring, Matt's going to come and tell you about a project that we're just getting started on.
What we're looking at here is, on the left, we have a Color Lovers image. And this is a template. You can find it on the Color Lovers website. Color Lovers also gives you the palette, which is the 5 colors in the middle. And now, our algorithm, you know, what our algorithm sees when it looks at this image on the left is we break everything into a set of color groups. And so what that looks like is what's seen on the right. We're just mapping each color on the left to the nearest pixel in the palette. And what's on the right does not look nearly like what the image on the left does. And this is sort of fundamentally how our algorithm operates, though, is by looking at these pixels and looking at adjacency in this very discretized space. And so this isn't perfect. The reason that we can get these nice recolorings that we've shown in the entire, or throughout the talk, is that we use the Color Lovers website, because Color Lovers directly maintains a much richer set of layers which have much richer color blending properties. And this is why the Color Lovers website, you know, we have these good recolorings. There's blending. It's not just the 5 colors, it's a blend of the 5. And that blending is very important. So what's going on behind the scenes in the Color Lovers website is that we have the input image here from the Color Lovers site. It has a decomposition of this image into a set of layers, or we call these color groups, but in general these are floating point maps. They're sort of like what you would expect. The 5 colors, a linear combination of the 5 colors, gives you the image on the left, and then if we change these 5 colors around, recombine, resum the image, we get the layers on the right. And so what's, you know, this entire website, most of what we, or this entire talk, most of what we've given you are colors, or patterns from the Color Lovers website. And these may not look like the patterns that you're used to seeing. The real question is, what we want to do is move away from being restricted to, you know, these websites where someone has carefully given us the entire layering. And we want to operate on real images that you see in the real world. Photographs, artistic paintings, whatever you have, things made in Photoshop. So what we want to do is take the image on here, and we want to break it up into a set of layers, just like the Color Lovers website does. And so here, these are 5, we pick the palette of 5 colors, and then we can want to construct these layers. And again, the linear combination of these colors gives you back the original image. But of course, the idea is that what if we change the fundamental colors in the image, then we can get recolorings, which dramatically change the theme or mood. And part of our whole work is in, we've presented you lots of different ways throughout the talk of generating these colorings, and moving forward just trying to take the more restricted universe of Color Lovers pattern templates and generalize it to a much broader set of colorings. So let's look at these in a bigger picture, or larger, so that you can see what we've done. This is the original image. This is the 5-color palette on the right. You may be wondering, how do we pick the right number of colors? We don't have a great technique at the moment. We try a bunch of colors until we get one that represents the degrees of freedom that we're looking for. So here what we've done, original input, broken it into layers. And then if we change those colors, we can turn it into something else. This is a sunny day theme. This is, perhaps a darker, thunderstormy day. Or you can do weird things, red, white, and blue patriotism, whatever you feel like. And the idea, moving forward, is trying to generalize it so all the same techniques can apply, but to a much broader class of images, and hopefully a broader class of applications. So here we've shown you on some concept art from Magic the Gathering, but it works on many other types of approaches. This is recoloring a sunset image into a sunny image. And here, we've done some art of an artist that I don't remember the name. But in general, we found that it works on a surprisingly wide range. And so this brings us to 2 important questions that we're looking at right now. The first is, of course, how do we do this decomposition? Here we have an input image, and we'd like to be able to decompose it into these layers. That's not completely trivial. We'd like these layers to be semantically meaningful. We have lots of constraints that we would like in order to get good results. And then the other very significant research question, which is directly relevant to the whole talk that we've been giving so far, is given a layer decomposition, how do we apply the formalism that we've gone through in order to suggest colorings for the images on the left? The idea is exactly the same. These layer decompositions are exactly the same thing as the color groups that we've been using before, that were on the Color Lovers website. But the color groups were very discrete regions. The idea of the shape of a color group, we had lots of ways of defining it. We have to generalize all of those ideas into a broader sense. But at the end of the day, we hope to just reduce it to a factor graph, where this factor graph encodes adjacencies between the layers, come up with new factors which are analogous to the continuous factors, analogous to the discrete layer factors, and apply the exact same formalism to automatically recolor in hopefully a useful and meaningful way real images found in the web. Okay, Daniel is going to finish us off on the last slide.
Great, okay. Right, so taking a step further back and looking farther toward the future, we think that sort of automatic color suggestion is really just the tip of the iceberg here, because when you think about it, color choice is really just one of many different important attributes in visual design. Other critical properties include things like layout, typography. If you're trying to visualize data, there's the choice of what marks you use to visualize that data. And we think that the probabilistic framework in general that we've sort of presented in this work is general purpose and should be able to be productively applied to these kinds of areas as well. So, kind of ultimately in the long term, what we're looking at is sort of this future of computational visual design, where we have these probabilistic suggestion engines that are working in tandem with people to try to create more communicative or more beautiful graphical artifacts. And that's the end of our talk. So thanks for your attention. If anybody had any other questions, we'd be happy to take them. Yeah?
Can you apply it to something non-visual like music?
Yeah, so I think we haven't actually looked at doing that directly, but there's another student in our group who's looked at trying to do automatic song composition using probabilistic inference. And I can't say that he's published anything on it yet, but it seems applicable. It seems like it can work to some extent. So That's about the most that I know on the subject. Yeah.
Nothing with the test where you have the 16 images that you were producing was a 13-point-something% in the bottom 4, whereas human artists were pretty close at 12-point-something.
Something like that, yeah.
What I note about that is it could be the fact that you had all these really, really awful colorings from the randoms mixed in, which makes the, because those absorb so many of those, yes, you do end up with a relatively close percentage there. And so I would suggest that you may not be near that close to the humans in terms of your percentage that go into the really bad bin, because the way your test works.
Yeah, it's an interesting point. Yeah, there's definitely a lot of other possible experimental designs to evaluate this kind of thing that we've only really looked at one point in the design space, and I think that, yeah, the experiment we've done is definitely not enough to say that we have said the definitive word on this subject. That's for sure. Yeah.
Artists have styles. You had 82 artists making 100 each or something approximately like that.
Yeah.
Are there groupings of styles, and then could you get something? I want something that looks like an impressionist would do, versus I want something that comes from the 1500s.
Yeah, that's interesting. We haven't looked at, say, trying to do some kind of automatic clustering of all of the data and seeing sort of what types of styles naturally emerge. But that is an interesting possible way to present an interface to the system. I think the way that we looked at it for this project was just imagining someone looking at some artist online and saying, I like the way this person does colorings. I want to generate something that looks like what they do. But that would also be a really interesting way to look at it too, I think. I see lots of hands. Go ahead.
You're playing like in the imaging in the future kind of idea. So like intensity keying to the colors. So like they do with chroma key, but with intensity, so that when you colorize, you borrow the intensity from the image.
Oh, I see what you're saying. Yeah, so sort of factoring out intensity from the chrominance and just doing recoloring on that as well. Yeah, that's also something that we could look at. We haven't done that as well, but that's a good suggestion. Yeah.
So I saw you guys were doing a little bit of work with 3D meshes. Were you taking 3D data into account, or was it just on the 2D texture?
No 3D data, no. It was just the 2D texture. To be honest, that was kind of an example that we put together pretty last minute. But it would be interesting to look at 3D spatial information as well. There's no reason you couldn't incorporate it into the probabilistic model. But since the main focus of the work was on these sort of 2D images, that's sort of where we stuck for now. But yeah, totally.
So a suggestion more of a question. In rule-based systems, a good counterexample is worth 100 good rules. So is there a way to adapt Metropolis Hastings to use counterexamples that say stay away from this part of the space and stay away from it real good?
Eating had a paper on, or working on that.
Oh, yeah. So I think the answer is yes. I think that should be possible. We don't yet have the definitive word on how you do it, but it seems very possible to do.
All your bad random ones.
Yeah, exactly. Exactly, yeah. Definitely.
Were there some features that you thought would have been useful that you kind of threw out of the model?
That's a good question.
Yes.
Yeah, there were. I think it's been a while since I've looked back at all that stuff, but I think there's some more description about that in the paper on which ones didn't end up being as useful. I know there was some of the stuff with the color names. There were a few different features that were based on color naming and name saliency that we used, and only like one of those ended up being useful. We thought more of them would be.
Yeah, so I think it was the names. Was it the name distance between adjacent regions? So I was seeing if one region was in a different color category than another. So if one was red and the other one was green, it would say those regions don't overlap at all in category space. On the other hand, if it was red and dark red, then there's some overlap because they're both red. And we found that that factor didn't really have much weight in the model, though that could also be because actually color namespace is actually pretty large, and there's a lot of like zero values there, so it might be that it couldn't handle that type of factor very well during weight training.
That's true.
On the other hand, we did consider like looking at hue differences, but in the end we didn't add that to the model, and that's something that color name distance is sort of similar to that, but it doesn't handle. So if we see something like red and yellow, it'll still think that distance is 1. But I think as people, we kind of think of red and yellow as being closer together than red and blue, even though they're not really in the same category. So that could be something to look at again.
Sure.
Can you account for perception differences for color blindness, for example, if you were doing this not for patterns but for other kinds of displays, like big data visualization, for example?
Yeah, it's certainly possible to encode those kinds of terms in a model like this. We haven't looked at doing it, but it's definitely possible to do.
What about templates that are slightly that are similar? Can you identify similar looking templates, or for a template of a flower that is slightly different, can you use the previous data to
Identify it in what sense? Like, I'm not quite sure I understand.
I mean, the template you start with.
Yeah.
If there's another template which is just slightly different, do you need to train with those images again, or can you kind of identify some similarity between templates that you start with?
So the algorithm actually is very good at that. It generalizes it, like we don't train on a specific template and then generate colors only for that template. Kind of the whole idea of the work is that we can take color patterns, which are very different. The templates don't have to have much relationship to each other than that we can break them into color groups and express the relationship between those groups. And so we can train on, a bunch of pictures of birds and then use that to color a bunch of pictures of clouds. Now, that works because in Color Lovers, the templates all sort of have discrete regions, and we can look at them specifically. If we started generalizing, which we're very interested in doing, to Flickr, let's say, where we start training on 10,000 or 10 million photographs, then we get into a bit of trouble because it might be difficult to start taking like beach recolorings and using them to recolor something completely unrelated, like pictures of conference rooms. It's not good to generalize too far. In the case of Color Lovers templates, they're all very stylized, and we felt at least that it was sufficient to generalize across all the templates.
Fair enough. Yeah.
It seemed like the random patterns is reminiscent of late 60s, early 70s mod style. Is that because they were breaking convention in some sense, you think? And have you tried doing
That's a good,
some of those
I think that one reason for that might be that those styles often use extreme saturation. Bright neon green was very popular because it was hard to generate too much else. You only had 256 colors, and whoever picked the initial color palette in those days. And in general, we found that like bright neon colors are not as desirable.
Or at least they're hard to make look good with other colors, at least.
Correct. Yes.
That's true. Yeah.
Your examples tended to go towards abstraction, and except for the demo where you had an example of a person. With people get their colors done so that they have hair color and facial colors and all, and then they match, and then you change clothing on them. How well would you do versus there are people that make a living coming out with color palettes for people.
Right, yeah. Well, I think the point of the project is not to try to replace those people. It's just to try to give them tools to see things they might not have seen before, and to make it easier to explore opportunities they might not have seen. My guess is, the fully automatic color suggestions are not going to be the same quality as what someone who's been highly trained and spent a lot of time doing this is going to come up with. But if they have the ability to look at a bunch of different suggestions, we think that that's very valuable for helping them sort of explore new ideas they haven't thought of in the past.
I think it's particularly valuable for people who might not be experts
Right.
in the area.
Right.
And I think people generally find it easier to, like, if they see a bunch of options, judge whether they like it or not, rather than generate something from scratch.
I was suggesting this because there's actually a well-known evaluation function that you could be applying. There's a ground truth on how well your system would be doing versus that ground truth.
For that particular domain, you mean?
Yeah.
Yeah, that's a good point. Definitely. Yeah.
So that sounds like if you were trying to generate something for an amateur, you'd want to generate relatively few suggestions, whereas if you were really trying to generate something that an expert hadn't thought of, you'd like to generate a wide variety of.
Yeah, I think you're definitely getting at the notion that I totally agree that an interface for experts to this technology would look very different than an interface to casual users. Whether or not you'd want to go with few suggestions versus more, or maybe a hierarchical suggestion versus a flat, I'm not really sure what it would look like yet, but that sounds like a reasonable suggestion.
In order to learn the preference of the user, have you thought about doing a ring around approach?
Can you elaborate on what you mean by that?
Ring around is where you have your picture, and then in a ring around it, you give different interpretations. Someone touches the one that they like the best, and then based upon that input, it then recalibrates and generates another ring of recommendations. And there, in a couple of clicks, it can learn your preferences and give you highly personalized appearances.
Yeah, I mean, it sounds like a good idea. We haven't really explored very much in the interface space to this technology. I mean, the work that we've done has mostly just been the algorithm, sort of the back end to it. And the demo that we showed is just sort of one initial prototype of how you might interact with this stuff. But I agree, there's a lot more sort of front end work that could be done.
I do have a question about that front end. So how much of that did you implement there? I'm assuming it was JavaScript, or?
Yeah.
Okay.
Yes, so the demo was actually made by some undergraduate students who were working with us over the summer. And a lot of it was actually built off of this open source vector art tool called MethodDraw. And we used JavaScript to, I guess, hook up the color suggester and add additional constraint tools.
And so you were using data that was generated from a separate backend tool?
Yeah,
just
so
loaded in
we
there.
just used Ajax to call this
Sure.
backend
Cool.
to get suggestions.
Yep.
During training, you construct probability distributions for lightness and saturation. But those are not joint probability distributions; those are separate. Is that correct?
That's right. It's true that we definitely compute a bunch of these sort of separate individual distributions, and then we multiply them all together with weights to get the sort of full distribution. And we are making very particular independence assumptions there, which are probably not true if you look at the sort of global truth of things. That it's sort of a simplifying model assumption that tends to work out okay, but your mileage may vary.
If we felt that we had enough data, and we may have for some factors, you can always merge the two unary factors into another unary factor, which is a joint one. We never got to the point where we felt that that was going to benefit our results, but if we start training on Flickr and all these things, then we may get to that point one day.
Yep.
Especially for take the two most popular features, are the ones that are most indicative and most successful, and try it for those, and we would see if the results got better. We'll be happy to answer questions after as well, if we want to take some.
Yep.
Thank you.